So here is a mail from Atul Das, and the mail was written on 19th of May. Atul, I am sorry I am replying so late. I have piled up a huge backlog because so many mails come every day. I am not able to answer them, and your mail I read only recently. So this mail is about Faraday's law. In fact, he has asked 3 questions. I am only answering the first one. He says that Faraday's law is defined for a closed loop. Then how do we define motional EMF where a rod moves in a magnetic field, B field? So, first of all, Faraday's law is defined for a closed loop. This is not very correct, although this has no connection with the answer of this question. Faraday's law is point by point relation, and it is relation between the changing magnetic field, if at all the magnetic field changes with time. So changing magnetic field, rate of change of magnetic field, and the induced electric field. Changing magnetic field creates electric field, and Faraday's law is to connect these two, the electric field created by a changing magnetic field. And there is a point by point relation. But if you apply this Faraday's law in a circuit, then yes, integral of electric field dot dl vector. That means you just take this line integral around the circuit, the induced electric field, and then the line element along the circuit. This integration around that circuit, that is EMF, because this induced electric field drives the electrons in one particular direction. So this induced EMF turns out to be equal to rate of change of flux d phi dt. That is the stated Faraday law in schools. At class 12 level, we define or we present Faraday law in this fashion. That's true. Now, coming to motional EMF, how does motional EMF result? Motional EMF result because when a metallic rod moves in a magnetic field which may not change in time, then the electrons of that rod, they also move with the rod, and then on the moving electron, this magnetic field exerts a force, and that can separate the electron, that can push the electrons on one side of the rod. So eventually if the motion continues, then you have a charge distribution on the surface of the rod, more negative charge on one side and more positive charge on the other side, and the magnetic field through this QV cross B force maintains that separation. Okay, so that is how the motional EMF is obtained. Now it so happens that if this moving rod is part of a circuit, once again, if it is part of a circuit, and on that whole circuit, if you calculate how much is the rate of change of flux, B into dA by dt, A is the area, because B is not changing in my example. So that is the rate of change of flux. That happens to be equal to the EMF. And what is that EMF? That EMF is because of QV cross B. That force is separating the electrons. So although in both cases the same equation works, EMF is equal to d phi minus d phi dt, that works in both cases, but then this has nothing to do with the Faraday's law. Motional EMF has nothing to do with the Faraday's law.